Okay, so you have the positive ions of the metal with their valence electrons already lost. And the positive ions are floating in a sea of electrons, sea of the valence electrons that have come off. So what's holding them together is this positive is attracted to that electron, which is attracted to that positive, and that's what's holding them all together. Those can you tell which electron went with which positive ion? It doesn't matter in holding them together which one is attracted to which. No. So, and group 2A has positive 2 charges, but more protons. So, in a sea of electrons, those electrons are free to move in the solid. Okay, so there's our picture of what a metal looks like. So it says that the electrons are free to move. Well, electrons are charged pieces. Charged pieces that can move. That's why metals conduct electricity. Metals conduct electricity because the charged pieces can move. The electrons, charged pieces, can move. So if I were to put a negative charge over here, these electrons here would not want to be next to that negative charge. So they would move this way. Everybody okay with that? And that means if I move them this way, that means there's going to be more negative here, which is going to push that one that way. It's going to push that one that way. And finally, I'm going to have a whole bunch of electrons sitting out here. So I started off with a negative end on this here, and I got all the electrons piled up over here. So this ends up negative. So the charge moved through the wire because the electrons moved, which is different than how ionic compounds do it, because ionic compounds, that whole positive ion has to move. And there's not a negative electron, there's a whole other negative ion that has to move. So it's harder to get the pieces to move in an ionic compound because they're much bigger. Metals conduct electricity because their free-flowing valence electrons allow charges to move through. So that's what's happening at the power plant. It's making a charge, pushing electrons one way, and then a fraction of a second later, it turns this into a positive charge. And then all the electrons start coming back. And when the electrons leave this end is left positive. And that happens 60 times a second in the wires coming out your wall. So the electrons are going this way for 1/30th of a second, 120th of a second, and then back the other way for 120th of a second. Alternating current. And all that's happening is electrons are going back and forth inside the wire. So the electrons you're pushing at the power plant are not the electrons you're using to light the light bulb. Does that make sense? And that's different than what ionic compounds do. The whole ion has to move, so you got to melt the whole thing. If you melted metals, the electrons could still move. Okay? So melted metals would conduct, because the electrons could still move around. Another thing we said that metals are malleable. that if we hit them with a hammer, they would change shape, that they would bend before they broke. Has that been your experience with metals? Metals dent before they break, right? China does not dent before it breaks. You've never found a piece of dented china. Okay. We're going to explain why. We've never found dented china. Okay. The other thing we said was closely related to that was ductile. They could be drawn into wires. That was they stretch before they was working just a minute ago. What happened? Okay, that they stretch before they break, like taffy, except you got to pull a lot harder. So stretch before they grow, before they break. And the sea of electrons explains why that can happen. Okay? So if I got a piece of metal, the electrons are arranged like that. If I grab a hammer and hit right here, it would push those top, you can push that top row of atoms around. But are the electrons attracted to specific atoms? Can you tell which positive ion that electron came from? No. Is it stuck there in one spot? No, it can move. So when the atoms move, the electrons can move with them. And that makes them flexible. The metals are flexible because the electrons can move along with the positive ions. So the electrons allow the atoms to slide by each other. Electrons allow the ions to slide by each other. If I were to squeeze this, push on both sides, the atoms could come together and still keep the electrons in between. Metals bend and squeeze and stretch because their valence electrons are free to move and still hold them together. That's why metals dent, because if they dent, the atoms can move and still stay stuck. China doesn't dent. Porcelain doesn't dent. Ionic solids do not dent. Ionic solids are brittle. And the reason they're brittle has to do with how they're formed as solids. They form in a regular, repeating, three-dimensional arrangement. Everybody okay with that? I mean, metals actually have a crystal structure too, a regular repeating arrangement. They do. They have the same kind of crystal structure, but their crystals are held together by flexible pieces. The negatives are flexible. Are these negatives able to move around? No, they're whole atoms now, aren't they? So if I do that same thing, if I hit the top row with a hammer, when they slide by, the first thing that happens is the positive aligns with the positive and the negative aligns with the negative. As soon as I start to slide them, I get the same charges next to each other. And what happens when you put the same charges next to each other? They repel. So you try to slide it across, it doesn't slide. As soon as it starts to slide, the only option it has is to repel and break off. And that's why China breaks as soon as you hit it with a hammer. It's because you're trying to slide them past each other. As soon as they start to slide, you line positive with positive, and it repels. It doesn't fall apart, it gets pushed apart. Yeah. It doesn't fall apart, there's actually a push. And when you go back, if you ever had broken china, you can tell when you got it back together right. It fits really well, right? You're getting those opposite charges to line back up. So, at strong repulsion, when you slide those positives next to each other, is what breaks the crystal apart. So this is somebody else drawing it. So we start off with them all lined up, but as soon as you slide them, put the same charges next, you get a repulsion. They don't fall apart, they get pushed apart. Fall just means they're no longer attracted. They're less than no longer attracted, they're actually pushed. Okay. So if you put a metal with a non-metal, you make an ionic bond. If you put a metal with a metal, you make an alloy. Okay? Alloys are mixtures. Another name for solution is mixture. Almost none of the metal you see is purely that metal. Most often, it is mixed with other elements. Now, gold rings are not 100% gold because pure gold is too soft. They put other metals in to harden it. Okay? Now, do they do that while it's a solid? Nah. You melt them together and then cool them off. Right? You got to melt them first. And actually, that was the first transition in civilization's evolution. We talk about the Stone Age, and next is called the Bronze Age. And what bronze is a mixture of copper and tin. But the reason why they call it the Bronze Age is because man stopped just using what he found in nature, the Stone Age, and went on to improving the materials that he was using. He was mixing metals together to make a better material, bronze. And bronze was harder than copper or tin. Okay? So they melt the copper and tin together, cool it off. There's some alloys we can't make on Earth. That's one of the things that some of the things they're checking up at the space station, is we can't mix aluminum and lead and make a good alloy on Earth because lead is much more dense than aluminum. So if you pour the two together, the aluminum floats to the top, the lead sinks to the bottom because gravity separates them. But if you do it in space, where it's weightless, you can mix them because there's no gravity to separate them. And you can make alloys in space that you can't make here on Earth. Okay. Now, size matters because they do have a pattern. And if the atoms of the two different metals, if the atoms are about the same size, they can substitute for each other in the pattern. This is called a substitutional alloy. Because you make that alloy by substituting in the pattern. So for example, if I got metal A and metal B, you can see they're not quite the same size, but they're close in size. So that if I make the alloy, metal B can fit into the pattern of metal A. Doesn't fit perfect, but that's a substitutional alloy. Is there any pattern to where the Were they mixed? No. So it's not like making a molecule, like making an ionic compound where you got to mix exactly the right pieces. You can mix these in any proportion. Okay. Substitution. But let's think about when we go to use our malleability. As I try to slide those rows of atoms past each other, they're bumpy. They're different sizes now. So as they try to slide past each other, they're bumpy, and it's hard to make them slide. So alloys are harder than the metals they come from because you can't get the pieces to slide past each other. Because as they slide past, you run into a bump. And we know as you're trying to slide a box across the ground, you don't like bumps. They stop you from sliding. Does that make sense? So if I tried to slide those two, so bronze is a mixture of copper and tin. It happens that in the Mediterranean, the two are found in, I think it's in Crete. It mines right next to each other. So it makes sense that it would be easy for them to accidentally mix them. Okay. Brass. Brass is about 60% copper, about 30%, about 40% zinc, and about 1% tin. You can change those proportions, okay, but that's what brass is. Gold, 18 karat gold. 18 is 18/24ths, and 18/24ths is 3/4. So 18 karat gold is 75% gold, 25% silver or copper. 14 karat gold is 14/24ths, 7/12ths. 12 karat is 50% gold, 50% other. But it's a substitutional alloy. The reason why you do that is because you don't want a 24 karat gold necklace because it's soft and it bends really easily. You can dent it with your teeth easily. You can bend it with your fingernail. Your fingernail will leave a dent in pure gold. It's not something you want to make jewelry out of. Okay. Now, if they're different size atoms, completely different size atoms, the small one will fit in the spaces between the big one. So let's think about it. If you had a box of oranges, right? You had a box of oranges. You could pour sand into that box of oranges and not change the volume of the stuff in there, because the sand would fit in the gaps where the oranges didn't quite match each other. Okay? So where round things come together, there's a space in between. That space in between is called an interstices. So intersection is where they run into each other. Interstices is the empty space in between. So they call these interstitial alloys. It's called interstitial because that blank space is called an interstices. Okay, so we got metal A and metal B. Now they're not anywhere near the same size. Right? Metal B would not be able to take the place of metal A in the pattern. Can everybody agree with that? So what's going to happen if you put them together is the metal A is going to have gaps in between. The metal B goes in those gaps. It goes in those spaces. Once again, that makes it bumpy. Okay? So that makes it harder. Makes it less easy to dent. The most common example of that is the difference between cast iron and steel. Okay, so cast iron, it's called cast iron because that's how you make it. You make a mold, and then you melt iron, and then you pour the melted iron into the mold and let it cool until it turns into a solid. That's cast iron. Okay. Now, what happens is when you're making that, when you're melting that iron, they use coal to heat it. Okay? Usually burn stuff to heat it. And that burnt stuff gives off carbon. The carbon gets into the iron, and so you have a high iron content in cast iron, 4%. And so it makes a lot of little bumps, which is going to make it harder, but when it does slide past each other, it's more likely to break when the bumps are big, when there's lots of bumps. So cast iron is harder than iron, but it's brittle. So in Michigan in the wintertime, we make sure we put in antifreeze, because if the water freezes, it's going to expand and crack the engine block. The engine block is cast iron. Now, when they first started making railroads, they made the rails out of iron. They made the bridges out of iron. What's a problem when you make a bridge out of iron? If something hits it, it doesn't dent, it breaks. And then that track is broken, and the next train crashes. Or the bridge falls down. Actually had bridges fall down because they tried to use iron to make bridges. It was hard enough, but it was brittle. Brittle is not something I want in my bridge. Okay? Because if it bends, at least I can gradually fall to the water. Right? I don't want the sudden impact. Okay? So, at the time, there was steel. The only place you saw steel was in swords. Okay? And how they made a sword was they took a piece of iron, cast iron, they cast a big blot, and they put it in the fire, and they got it red hot, and they hammered it until it was flat. And then they'd fold it over, so what was on the outside was now on the inside. And heat it up and weld it together with heat, and then pound it flat again, and fold it over. And he put in the heat and pound it flat. They kept getting and every time they stuck it in the fire, any carbon that was on the outside got burned away. And then you would fold the iron without carbon into the middle. So gradually, your percent of carbon went down, and your cast iron became steel, which was both strong and flexible, didn't shatter as much. So there were blacksmiths, people who worked with cast iron, and there were swordsmiths, people who turned that cast iron and made it into steel. Okay? But there's a problem with that technique if you're trying to build a bridge. Imagine how hard it would be to build a bridge out of steel if you had to do that for every single piece of metal. Had to fold it over a bunch of times. Okay? So it wasn't until the late 1800s they found a way to make the secret was that you'd melt the iron in a big container and then blow air through it. If you blow air through carbon, CO2 came out of CO2. So you could get rid of all the carbon. And then you could put back in exactly what you wanted to put back in. So the goal was to make it pure iron as melted, and then add stuff back to make steel. Rather than trying to take out just the right amount, get rid of all of it, and put a little bit back in. So there are millions of steel recipes. They all start off with melting it till it's liquid, and then you can add, if you add cobalt, cobalt stops it from rusting. Or chromium. Chromium starts with rusting, you get stainless steel. Okay? So, an alloy is just a mixture. Okay? An alloy is just blending the properties that you have. The difference between 18 karat gold and 24 karat gold, 18 karat gold is harder, but it's not as shiny. Not as yellow. Why can you mix them together so easily? Because they stick to each other the same way as they stick to themselves. It's just metallic bonding. It's just metallic bonding. Okay. So that the metals sit next to each other, lose their valence electrons. Doesn't matter whose valence electrons are next to you. So gold sticks to copper just as the same way gold sticks to gold. Those loose flowing valence electrons means you can put them in any pattern, and they're going to stick to each other just as well. Ionic compound has to be in a specific pattern because you got to get that alternating positive and negative. Almost all, you don't use pure metals. You use alloys that were designed for a very specific purpose. So that's what ionic compounds were. The kinds that aren't ionic or molecular. Okay. Now we're going to recognize a molecular because they won't have a metal. Remember, ionic was metal and nonmetal? Alloys were two metals. Molecular is just nonmetals. We'll have to figure out later how these nonmetals stick to each other, because our technique with ionic bonding won't work if they're both gainers. That's next unit. The next unit is how these stick to each other. Okay. But they're going to be, since they don't have positives and negatives, they are going to be insulators as a solid, a liquid, or even dissolved in water. We saw that sugar didn't dissolve, when dissolved in water, didn't make the light bulb come on. They're going to have low melting points. Fact is, everything that you've seen that's a liquid or a gas has to be molecular. Unless you've seen mercury, which is a liquid metal. I'm fairly certain you've never seen liquid bromine. Liquid nitrogen you may have seen, but that was really cold. Hey, now they make crystals too. But they make two kinds of crystals. One is a molecular solid, where one molecule sticks to another molecule. Water is H2O. Ice is H2O, hooked to H2O, hooked to H2O, hooked to H2O. Sugar is C11H22O11. Rock candy is C11H22O11, hooked to C11H22O11, hooked to C11H22O11. Those molecules repeating in a crystal. And then there's one where it's a network. It's called a network solid, where every single atom is bonded to another atom. It's not just one, but the bonded ones attracted to other bonded ones, but bonded ones bonded to other ones. Everything's bonded. So, examples of network solids. Where every element is bonded to each other, that it's really just one big, huge molecule. One of the ones that occurs most on the Earth is SiO2, quartz. And quartz, its formula is SiO2, but this is how they're hooked together. The silver ones are the Si's bonded to O's, the red ones. And if you count, there's twice as many O's as there are Si's. But an Si hooks to an O, which also hooks to another Si, which hooks to an O, which hooks to another Si, which hooks to an O, which hooks to another Si. See how they're all bonded together? Okay. So a piece of the little grains of sand, each one of those grains is really just one big, huge molecule with millions and millions and millions of atoms because they're all bonded to each other. Diamond. Diamond is pure carbon. Okay? Diamond is pure carbon, where every carbon is hooked to 4 other carbons. Graphite. Graphite is also pure carbon. So how can they both be pure diamond how can they both be pure carbon? Come on. Open up. Can't get to work. That's what I wanted. Okay. So on diamond, well, it worked just a second ago. Okay, so this is diamond. Okay. And on diamond, every carbon is hooked to 4 other carbon, so you get a network where everything's hooked together. So this is graphite. On graphite, every carbon is hooked to 3 other carbons, and you get layers, flat layers. Okay. Everybody see the flat layers there? Little hexagons? So it's the way they're connected to each other that makes diamond and graphite different. They're both pure carbon. They're both network solids. Glass. Glass is silicon dioxide, just like quartz. But glass was cooled in a way that it didn't get a chance to make crystals. So it's not quite a solid. It's still kind of a liquid. And since those SiO2s are not in a pattern, you can break it in any direction. Glass shatters in every direction. But you see those crystals hanging from people's mirrors? Those are quartz, and they're always hexagons because they grow as hexagons, and if you cut them, the only place they're going to break is at the angles that makes hexagons, because everything is hooked in a hexagon in quartz when everything's arranged. So glass is random SiO2, quartz is patterned SiO2. So to make glass, you melt quartz, you melt sand, and throw some stuff in there when it cools off, won't let it turn quite into a solid. So covalent bonds are stronger than the attraction between molecules. So network solids are hard. Diamond, the hardest thing known to man. Graphite. Graphite is really, really stiff and rigid. That's why they put layers of it together with glue and have them at different angles so that you can make graphite baseball bats. Carbon fiber is graphite with some glue attached. Network solids have high melting points. Now with graphite, there's one place that really tells us that it's that's what it's like, and that is, okay, on the graphite, this is what you're doing when you write with the pencil. You're wiping layers off. Actually wiping layers of carbon off as you rotate it as you write with a pencil. Graphite in your pencil. They can use it as a lubricant in locks. So if you're locked, to lubricate a lock, you don't want to put anything wet in there because that'll attract dust and clog it up. But if you spray dry graphite in, any place where the graphite is pinched, the layers of graphite will be able to slide past each other. So it won't get clogged up and get sticky, but it'll be lubricated. So graphite makes a good lubricant because the layers slap by. Diamond is not going to make a good lubricant because in a diamond, diamond is the best insulator because every single carbon has got every single electron bonded to a different carbon. So that's the 3 types of things we need to worry about. Ionic compounds. With molecular, we got to worry about whether they're just molecular or whether they're network solids. And that's the material for this unit. We have a lab tomorrow. Dress appropriately. Well, we'll see. We have a lab on Wednesday where we'll see these. We'll start reviewing tomorrow for our test on Thursday. We okay with that? The notebook list, review sheet, pre-lab, all that stuff tomorrow. And then on Tuesday, or